Hello, everyone. I hope you hear us well. So we will get started. Welcome. So it's my pleasure to welcome you on this side event titled "Future Mountain Groundwater Resources: Identifying Challenges and Guiding Science and Practice." My name is Clément Roch. I'm a scientist at the Center for Hydrogeology and Geothermics at the University of Neuchâtel in Switzerland. And I'm honored to co-chair this event with Monica Tolotti from the Fondazione Edmund Mar and with Elisa Leo from Legambiente Piemonte e Val d'Aosta. Before we begin, I just wanted to inform you that the meeting is recorded and the recording will be made available online by the main organizers. If you can go to next slides, Elisa. And again, next slide. Yes, so we would also like to highlight that this event is organized within a project, within the Waterwise project, co-funded by the European Union through the Interreg Alpine Space Program. The project aims to tackle current challenges in water management in alpine headwater, so we are clearly in the topic of today. So if you want to know more, for more information, feel free to visit our website and follow us on social media eventually. Okay, the agenda for today's session is as follows. I will give a brief introduction. Then we will go to an interactive questionnaire, a Mentimeter session to get to know a little bit more about you. And this will be followed by a panel discussion with our experts and leading into a Q&A session where you will have the possibility to ask questions and interact with the panelists. And we will, after that, go back to an interactive questionnaire where we aim at gathering your perspective on the challenges and recommendations related to future mountain groundwater resources. We will then discuss our plans to continue these conversations beyond today's event. Next slide, please. All right, of course, we know why we are gathered together today. It's because of pressing reality. Glaciers around the world are retreating at an unprecedented rate. And the 77th UN General Assembly adopted the resolution to declare 2025 as the International Year of Glacier Preservation and March 21st as the annual World Day for Glaciers starting in 2025. Today's event is part of this global effort. Next slide, please. We have the mission to raise global awareness about the critical role of glaciers, snow and ice in climate system and hydrological cycle. We need to emphasize the socio-economic and environmental impact of the ongoing change and identify the best practices to address the challenges posed by glacier retreat. Next slide, please. Of course, as you know, the water cycle is changing in our mountain systems. We are witnessing dramatic shift in the flow regime of glacier-fed streams. And in this context, there is a key but often overlooked component of these changes, which is groundwater, the water that is stored underground in the geological medium. This hidden part of the water cycle is also impacted by climate change and glacier retreat, as you can see on this drawing. But our current understanding of the feedback mechanism between glaciers and the cryosphere in general and groundwater remains limited. This gap arises from the challenges in monitoring groundwater, modeling its dynamic, and integrating it into management strategies. But despite these challenges, there are many promising actions and opportunities that are emerging from the scientific community, stakeholders and practitioners to better evaluate and model groundwater in glacier-ice catchments. Next slide, please. So today, we are fortunate to have three experts with us who will spotlight our current understanding of cryohydrogeological processes, drawing on insight from monitoring iconic glaciers, We will cover the implication of rapid glacier melt for groundwater recharge and downstream water and land management. We will also address critical data gaps and challenges in predicting future water availability in mountains. We encourage you to actively engage during this panel discussion by posting your questions on the chat. And my colleague Odile and Ronnie will be gathering your questions to our panelists. So next slide. Before we start the panel discussion, we would like first to know a little bit more about you. So we have prepared an online survey where we invite you to connect to either this via this QR code or directly on the Mentimeter website, so menti.com, and use the code that is displayed here. I believe that my colleague also posted it on the chat, so do not hesitate to look there. And we can move to our Mentimeter platform. Elisa, please.
Just a second, I'm giving time to everyone to connect.
Yes, sure. Excellent. So please connect to the Mentimeter. And then we will move to the first question. So the first question is, does your work or livelihood involve mountain water resources from glaciers? Please, so we leave some time for you to answer. So apparently we have many people that are concerned, most of us. Elisa, I leave you going through the slides when you think it's, yeah. And we would like to know, what is your primary area of expertise? Hydrology, climate, glaciology, ecology, biodiversity, socioeconomics, policy or decision making, or others? So mostly hydrology. Oh.
I was too fast, sorry.
No worries. So mostly hydrology, ecology, and socioeconomics. Thank you. So we can go to the next. And what type of organization do you work for? Academic research institution, government agency, NGO, private sector, international organization, or others? And finally, in which mountain region do you primarily work? So you can directly click on the map. On the phone is not so easy, but it's more or less to know where you are located. So mostly in Europe, one representative from the US. Thank you. So I think we can move back to the presentation, and we will come back to this Mentimeter at the end to know a little bit more, to ask you more detailed questions. So now I wait a few minutes for Elisa to share the screen again. and I can hand over the floor to my colleague Monica, who will moderate the panel discussion with our experts.
Yes, good morning, everybody. I'm Monica Totti from the Fondazione Edmund Mark, which is in Italy. And I am a freshwater ecologist, so I can provide you this perspective. So today I'm going here to moderate the discussion among panelists. We have 3 panelists, but before starting with the questions, I would like to remind that we have to take care about time. So each panelist has about 7 minutes to answer his or her questions. And I will remind to the audience that they can write questions to the panelists in the chat of these team meetings. So we will have time to discuss the questions and the answers later. So let's start with the first speaker, which is Bettina Schaefli. She completed her PhD at the École Polytechnique Fédérale de Lausanne in 2005, and on the simulation of climate change impact on alpine hydropower production. After her postdoctoral research stays in Germany and the USA, she became assistant professor on hydrology at the Technical University of Delft. And in 2010, she came back to Switzerland. And after several career grants, she was appointed full professorship for hydrology at the University of Bern in 2019. Her research currently focuses on quantification and modeling of hydrological processes with a strong emphasis on mountain areas. And so the first question to Bettina is if she could provide an overview of the role that glaciers and groundwater play in the hydrological cycle, particularly in sustaining stream flow in glaciarized catchments. Please, Bettina, the floor is yours.
Thank you very much, and thank you also for the invitation. So I guess most of you in the audience actually know pretty well how glaciers influence stream flow. So this is this very well-known strong annual cycle of stream flow due to the fact that in the winter we have accumulation of snow and in the summer we have melt of snow and ice. This is, in many places, this pronounced cycle is just like a nice thing to have. We have a lot of water in the summer, but we should not forget that in particularly dry areas, over the summer period, it might be the only source of water, the seasonally shifted melt of snow and ice. And so this very strong annual cycle, that's what we observe if we go out to the mountains or if we use that water. That's what we see in the stream flow. What we tend to not see is that the fact that ice melt and snow melt provides very high flow in summer also has an important role for recharging groundwater downstream. So this effect that the snow that accumulates in the winter and the ice that has accumulated over several decades provides high waters during summer, extends also to periods after the main melt, because there is a continuous interaction between the water that is stored in the surface, so the ice, and the water that is invisible, that is stored under the surface, the groundwater. And nowadays it's clear that we have a rather good idea of what is stored on the ground, so the ice, because we can observe it from space. Glaciology has made big progress in quantifying worldwide glacial resources. However, the invisible part, so the interaction with the groundwater, remains a key challenge to quantify. Because in many mountain areas, the fact that ice melt recharges downstream groundwater might well lead to the only source of water during really extreme low flow periods. When up in the mountains, ice melt has already stopped. We are going, for example, in autumn, in the cold season, but the groundwater continues to release the water that was recharged over the entire summer. So I hope this gives you an idea of the importance of ice melt in interaction with groundwater. In some places, like the pictures we see on the screen, we have done detailed study to understand this interaction. But on a global scale, this certainly remains one of the big questions. How much do we know about the importance of this interaction between glacier melt and groundwater?
Thanks a lot. A very clear explanation indeed, which also introduced partially and already the second question, which as you and the audience can imagine is about the role of climate change. And in specifically the question is, with the projections indicating significant glacier mass losses globally, what are the expected long-term implications for groundwater storage, discharge to streams in mountains? Of course, you already partially answered this question.
Well, so first of all, it's nice to recall like where we are now. So we are in this period where most glaciers worldwide are providing a lot of melt because of glacier retreat. So at many places we are in this period, this is called peak water, where we have more water now than what naturally falls in a year as precipitation. This is this legacy effect because the glaciers still provide water that was accumulated up to several decades ago. Now, in some places, we might well already be in the phase where, you know, the small glaciers have retreated and we have less water than before. And people now start noticing that at some locations, the stream flow has become much more variable because as long as we have a lot of ice melt in extreme dry years, the ice melt compensates lacking precipitation. And now people notice that variability goes up. And at the same time, the interaction between the ice melt and groundwater certainly still buffers the natural variability at many places. So we are in a period where in some local areas, we suspect that the retreat of glaciers increases natural variability. But we do not know what role groundwater plays in buffering the fact that ice melt has become less reliable. And of course, what I also always tend to say is that in most places, like in the Swiss Alps, where I work mostly, this surplus of ice melt in the summer is something that is really nice to have, especially for hydropower companies. It gives us additional water during dry and hot years, which is really nice. In other places, this glacial subsidy might well be the only source of water. Like I know the case of the northern Chilean Alps, where entire agricultural production depends on seasonally shifted glacier melt, and there is strictly no rainfall. And in these places, of course, the continuous retreat really questions the viability of current agricultural practices and also livelihood of people.
For sure. Thanks a lot. The discussion about the peak water is a very tricky one, actually. And this introduces also the next question, which is a more practical one. In fact, I'm going to ask you if from your field activities, do you have feedbacks on how our local authorities planning to future adaptation? Because you told that the question, so the people are starting to realize the new situation now.
Yes, so in Switzerland, typically the local authorities, they notice, you know, that the variability between the years is increasing, and the current answer to that is certainly to go out and monitor to better understand how much water there is. We have lived in this impression of abundance in the past, and the first step is really to know your resource. And this is like with simple things like monitoring soil moisture, for example, which many farmers have done already in the past, but simply also monitoring drinking water distribution. then there is this whole technical adaptation, which goes through the building of new reservoirs that could be used for several purposes at the same time, which of course is an economic question. If you can build new artificial reservoirs, and also an ecological question: where can you build them? Do we want to have them? And then, interestingly, it even goes to more radical adaptations, which are now discussed in Europe, which is, for example, the question if we have to limit the number of people who can live in a certain mountain area because there is not enough drinking water in the future. This kind of radical adaptation, of course, is not something that from a scientific view would encourage, but if it's discussed in public, it really means that there has been a change in the mindset and that people notice that the emergency is really starting.
Yes, we probably a cultural adaptation is much more difficult than a technical one. It takes more time and more larger effort. So many thanks to Bettina. And I think we can shift to the next speaker now, who is Nicolas Oestreicher from Switzerland, who completed his PhD at the Technical University in Zurich in 2022 on coupled hydrogeological and mechanical processes in Aletsch glacier catchment. He recently joined the Institute for Snow and Avalanche Research in Davos in Switzerland, where he investigated the initiation of large rock slope instabilities. There he will lead efforts to better detect, monitor, model, and forecast large rock and ice avalanches, including those involving glaciers and saturated sediments. So Nicolas, the first question to you is the following. So similarly to the last question, similarly, based on your research activities in the Aletsch Glacier, could you please provide us with an overview on the context and current situation regarding glacier retreat? For example, what is the role of groundwater, or especially what is the role of groundwater on the hydrology of the catchment in general?
Yeah, hello everyone, and thank you, Monica. So the Aletsch Glacier is the one we see on the picture here, and it is the largest glacier in the Alps in area and in volume. So it has an area of 78 square kilometers, and it is retreating now at a fast rate. So there is a service called GLAMOS in Switzerland, where we know the mass balance for many glaciers, and this one lost, for example, 1.3 meters in the 23-24 time periods. Since the Little Ice Age and the start of the measurement of the glacier length, it lost already more than 3 kilometers in length. And it's even worse, actually, if you look at the bottom part of the glacier. So this is the one we see on the picture, because this one is lying at low altitude compared to the rest of the glacier. It's going down to about 1,700 meters above sea level. So this part is even melting faster. And I had a discussion with Matthias Huss at ETH Zurich, and he told me that the lower part of the glacier is melting about 6 to 8 meters per year water equivalent. So it's losing a lot of its volume. And therefore, it's also providing a lot of water into the Massa River, which is at the outlet of the glacier, and where there is a hydropower station as well. So it has a big impact for the region. And then you were asking me about the role of the groundwater in the hydrology. So groundwater is also very important in this valley. And we can see that, for example, in winter, like Bettina was saying before, when the glacier starts to stop melting, then the groundwater takes a big role. And there we see that we have moraine material on the slopes a little bit, but mostly we have bedrock. And this bedrock is highly fractured. We have large fall zones and also the foliation, which is going in the direction of the valley in the part that we see on the picture. And so this fractured bedrock is recharging. And then we see that it's providing also water to the Massa River in winter. And we could monitor the groundwater in this place because at ETH Zurich, where I did my PhD, under the supervision of Simon Löw, we could drill some boreholes, which is quite rare in mountain regions. And we had 3 boreholes in the slopes where we could monitor the pore pressure in the slopes next to the glacier.
Mm-hmm. Thanks a lot. And I see in this region an important challenge is also related to the slope instability, right? Associated with glacial retreat. The case of the moose flu has been a major concern for local authorities. But could you explain why glacial retreat contribute to slopes damage and how it impacts also the groundwater recharge and discharge processes? If there is a relationship, and also maybe with accumulation of water, melting water, like proglacial lakes or so.
Yeah, it's true, exactly. The most flow instability is actually one that is behind the picture. I think on the next slide, there is also a picture of it.
Yes.
And there we can see that it's a large slope instability that was reactivated in 2016. It was already existing before. It was well known already, but it was reactivated and started to increase its velocity. And this corresponds approximately to the time where the glacier left this part of the valley. So you can see on the picture on the left, the tongue of the glacier, which is about the place where the most flow instability reaches the valley center. And around this time period, the most flow instability increased its velocity for a short period of time and then decreased its velocity again and stabilized a little bit more. So is still about the current state now. And this is not true only for the most flow instability, but also for other instabilities in the region. We see that when the glacier is leaving the valley, the instabilities start to be more active and start to increase their velocities. And there are many ways how the glacier can impact the slope stability. One is obviously that you remove a lot of weight when you remove the glacier. So you also change the stress in the slopes. And in this way, you decompress a little bit the slopes. The fractures can open a little bit. You can increase also the size of the fractures. You can create new damage in the slope. And therefore, you can also weaken the slope to the points that they become unstable and that they fall down. Another way is also that the glacier has a strong impact on the groundwater and the temperature cycles that the slope is seeing. So when the slope is covered by a glacier, it doesn't see a lot of temperature cycles over the year and also daily temperature cycles. But once the glacier retreats and leaves the valley, the slopes start to have strong fluctuations of temperature and also pore pressure that they didn't see before. And these cycles can create an effect of mechanical fatigue, where again, you create new damage, or you increase the size of fractures, or you open the fractures a little bit and don't close them as much. And over time, this effect of mechanical fatigue can also weaken the slope and create large slope instabilities like the one we see on the picture.
Many thanks, Nicolas, for the very clear explanation about these key physical processes for the relationship of glacier melting water and groundwater. Now we can shift to the last panelist, who is James Thornton, who joined the Mountain Research Initiative in 2020 upon completion of his PhD at the University of Neuchâtel in Switzerland. His doctoral research focused on interdisciplinary physics-based numerical modeling for hydrological processes in complex alpine terrain. He also led the development of models to quantify the risk associated with extreme natural events like floods and tropical cyclones. He's currently leading research for the GEO Mountains, which is an initiative of the Group on Earth Observations, who seeks to increase the availability and accessibility of a wide range of data on mountain regions globally to benefit human societies and ecosystems. So to James, I would like to ask, what are the main challenges in monitoring and modeling the interactions between glacier, groundwater, and stream flow, especially in high altitude regions, please?
Thank you very much indeed for the invitation and for the question. I would begin by just underlining why we need such monitoring and modeling. This is really firstly to characterize and understand the systems, and then to develop predictions which are useful for society. So this could be, for example, to what extent groundwater changes may either help compensate or actually, on the other hand, exacerbate the changes in stream flow which will arise from declining snow and glaciers in mountains. And an overarching challenge in this context is that the systems are really complex. There are many different components to consider, not only glaciers, groundwater and stream flow, but also related components. We have to consider snow processes, we have to understand the bedrock geology, as well as vegetation-water interactions and so on. And we need to therefore obtain data on many different variables and bring together expertise from several disciplines who may or may not be used to working so closely together. Another aspect of the complexity is because of the inherently complex topography and geology of mountain regions. Most processes have very high spatial variability, and also many are highly dynamic, so change very rapidly in time. And this has certain consequences for monitoring. We have to monitor or obtain data at high spatial resolution and high frequency. And this comes, of course, with associated higher costs, especially in more remote mountain areas, perhaps in different parts of the world beyond the Alps and the Rockies. And such monitoring is hard to achieve over large areas. But it's, of course, the large regions which are of most interest for policy and for society. Just to continue, it's really important to be aware, and I'm sure many of the participants are based on their backgrounds, that many fundamental hydrological measurements, which we might actually take for granted in other settings, are associated with very high uncertainty in mountains. So, for example, especially when we have lots of snow and high winds, it can be very difficult to obtain unbiased measurements of precipitation. And we often don't have enough stations to capture spatial patterns, again, due to the inherent challenges of working in mountains. Similarly, estimates of our river discharge, which we have to derive from measurements of water level, are also very uncertain, especially at very low and very high flows. And of course, these high flows and low flows are of most interest to decision makers and managers of these regions. Likewise, we hardly measure evapotranspiration directly at all. More generally, as Bettina has already alluded to, we're seeing this growing gap actually between the amount of data which we can obtain related to surface variables, topography, land cover, glacier extents, and this is largely thanks to the advances which we've seen in remote sensing. But on the other hand, the amount of information and the quality of information which we have related to the subsurface, so soil types, the properties of unconsolidated aquifers, bedrock structures and their properties, we still have extremely limited information on these aspects across most of the world's mountains. And yet, of course, it's these subsurface components, as Clément mentioned, which directly affect the groundwater and therefore exert a strong influence on the hydrological cycles more broadly. We have to, for example, be able to even delineate where the groundwater catchment is. This could be different from the topographic basin. We could have subsurface inflows and outflows, so this is another challenge. And in terms of the modeling, coming towards the end of my answer, it again comes back to needing to integrate all of these different components, which can be very challenging to make useful predictions. Traditionally, this has involved sticking different models together, each representing a particular part of the system. So you could have a snow model, add that to a glacier model, and take the outputs and translate this into a near surface hydrology model and maybe also a groundwater model. This is how things have been done in the past. And of course, then if we're seeking to make climate change projections, then there are some challenges and uncertainties related to the climate models. For example, the need to do downscaling and bias correction to make these useful in complex terrain.
Very complex picture indeed, with a lot of challenges. And the second question to you is actually related to these challenges, because we would like to know from you what are the interdisciplinarity, interdisciplinary research efforts that are needed to better understand and address the uncertainty surrounding cryosphere groundwater interaction. So we know that we need to get more knowledge on these, but how is the question?
Yeah, thanks. So coming to the solutions and trying to thanks. Yeah, coming to the solutions and trying to be trying to be constructive. I think one step, and I think we've already made quite a lot of progress on this, is to bring experts from different disciplines together and try to establish this common systems-wide understanding and vocabulary, so that when experts are, they can then have meaningful discussions, and when they say something, they're referring all to the same thing, and they can understand also importantly how to share data with one another. So what kind of outputs and formats, data formats are required by people working on one aspect of the system, and how we can share information and data effectively between one another. Second, I think we need to somehow address this growing gap, which I mentioned, related to the subsurface data and information. And here there are several promising approaches. So, for example, we could develop more detailed three-dimensional geological models. There are various geophysical techniques which have promise, including some emerging ones like terrestrial gravimetry. There are now a suite of hydrological tracers which are very complementary to one another to characterize stream water source components. So where is the water in the stream coming from? Is it from snow, ice, groundwater residence times, subsurface and surface exchange fluxes? And this is not only traditional tracers such as stable water isotopes, but also, for example, noble gases. The third is really, I think, to develop more holistic and hopefully integrated numerical models which have this physics basis, which can integrate a lot of the different data which is available, which comes in different formats. Some of it is gridded, some of it is in situ, related to all of these different components, and which can then be used to predict various different variables and fluxes in time and space. So rather than having all of these different models, we could actually come together as a community and try to develop models which really are designed to simulate the entire system and overcome any challenges associated with these model coupling in a simple way, and then to capture these interactions and feedback mechanisms. And just lastly of all, of course, there's growing interest in data-driven models and machine learning, and I think there's really lots of opportunities to couple, for example, deep learning models based on neural networks with physics-based models, in situ measurements and remote sensing, to also make then really efficient, holistic predictions in time and space, not only in these very well-monitored research catchments, but actually much more widely across the world's mountains, which will then hopefully benefit societies who depend upon these resources.
Many thanks to you as well, and thanks to all the three panelists for the clear and very, very clear answers. And now there is time for the questions. If there are questions from the audience, I don't know exactly. Seems there is no direct question on the chat, but maybe some from the audience.
Maybe I can ask a first question. This maybe we launch the following ones. Thank you so much for your presentations and answer to this question. It was really insightful. One thing that I retain is that we need to have field observations. We need to have pilot sites where we gather together as an interdisciplinary community to better understand these feedback mechanisms. We hear a lot about observatories, critical zone observatories that aim to federate these disciplines around pilot sites. What would be your opinion? How do we need to develop this as a community? Do we have critical zone observatories that specifically look at this interaction between glaciers and groundwater? Maybe Bettina, if you want to start.
Well, right now I don't have the overview of what exists worldwide. For sure that, as you mentioned, the critical zone observatories, some of them are also located at high elevations. But the challenge nowadays is that these observatories mostly have like a main focus, like typical the critical zone, and then like has then tends to gather only a certain type of disciplines and scientists. And I think more than the question of, where can we build new observatories, can we sustain them at high elevations, is the question of really how are we going to do that? How do we involve also the local people? Really going into the kind of transdisciplinary research where we actively involve stakeholders, not just their needs, but also their knowledge about the natural system. And this truly needs more collaboration with people from the humanities, and not just like people like we are today, who have mostly focus on physical processes. But for sure there is no doubt that we lack really high elevation observatories, besides the few well-established ones that we have in Europe at very high glacier sites. Yeah, we need the ones that really focus on water resources, which is a different type.
Yeah, fully agree. Like strengthening collaboration with stakeholders, local community, and and people working on socioeconomics models. That's really really important to develop. Maybe James, you have some follow on this topic, yeah?
Yeah, just briefly, I think it could also be a challenge, and hopefully something which can be partly addressed through this International Year of Glacier Preservation. But I think also we can try to exploit existing infrastructure and build these more holistic observatories where at least we already have some long-term measurements as a starting point and some functioning infrastructure. And so one of the products which we developed through GeoMountains over the last couple of years is this inventory of, well, we hope it's all, of course, it's not all in situ monitoring, but it's relatively comprehensive. And I'll put the link in the chat, which just shows individual stations and networks and so forth. And these sites could be also considered potential, locations at which we try to establish these more holistic mountain observatories. We had some success also in Central Asia last year. We launched the Central Asia Network of Mountain Observatories, or CAMON, which brought together 5 sites where at least 2 or 3 components of the system are being monitored, often climate, cryosphere or glaciers and hydrology. And now we're trying to make this even more holistic, to consider socioeconomic aspects and ecology, and to establish also data and capacity sharing amongst these regional networks, which is really important as well to deliver consistent information for policy and decision making as well. So I think there's many opportunities, and we could, for example, do an analysis to see where we are most missing observatories, whether that be spatially or in terms of elevation or in terms of the different variables and components of the system, as well as, of course, the demand side, how many people depend upon these water resources, and you could try to somehow optimize this.
Yeah, thank you, James. I think there is a raising awareness about how useful is to develop this critical zone observatory. Maybe Nicola, if you have some insights about the Aletsch example, because they have a quite significant risk for the community, for socioeconomic as well, related to the landslide, with impact to the power plants and the downstream communities. Do you have any insight about how the community react and organize and adapt eventually?
Yeah, it's true that there are a lot of consequences. For example, if you have large slope instabilities, you can have a catastrophic collapse, and then you can have cascading events where, for example, you dam the valley, and then you have a lake, and then you have debris flow below. So some other possibilities which are a bit less catastrophic is that the landslide is providing a lot of sediments into the river. And the river, which is charged with sediments, will clog the dam, and the hydropower system is not working as efficiently as it should. And then you need to invest a lot of effort to clean the system. So there are a lot of challenging problems for the communities in the region. And I think this is going to be very important in the future as well, because the glaciers are now receding past a point that we called the Holocene minimum. And that means that the slopes that will in the next decades come up and come out of the ice will see the light for the first time in a really long time. And because you also have erosion by the glacier, some of these slopes didn't see the surface at all. So it's like you deepen the valley, and then once you remove the ice, the slopes see a new stress level that they didn't have before. You decompress, and the slopes will react stronger. This is what we see in models. So it means that we could have even more natural hazard in the future because we passed this critical points that the slope didn't see before.
Thank you, Nicolas. So is there any other questions from the audience? We have one apparently. If Odile or Ronnie, you want to read the question to the panelists?
Yes, we can. So the question is, do you think that for all the panelists, do you think that infiltration and therefore aquifer recharge is larger from snow cover melting slope than from a bar-grown slope exposed to rainwater only due to climate heating?
So I saw that this question has been asked by Charles Leblanc, with whom I worked previously. So I'm happy to try to answer. So it's a very good question. It's a key question actually for the future alpine or high mountainous water cycle. Do we have different recharge from rainfall with respect to snowfall? And the current answer is probably yes. But there are only like very small scale studies that show that really in high elevation catchments. So there are like lower elevation studies, meta-analysis that clearly show that if there is more rainfall, that there is less stream flow. But at high elevation, the question remains open, and because we need really go out there and observe, have equipment, snow lysimeters that measure how snow infiltrates. But in principle, this nice continuously spreading out melt behavior of snow should be much more efficient in recharging groundwater than intermittent rainfall with high intensities. But that's work we hydrologists have to do.
It's a challenge, yeah. Yeah. Thank you so much, Bettina, for your answer. Is there other questions in the chat? Otherwise, we need to move forward. I don't see the chat, no answer. So I think we can go to the next slide. Thank you again to all the panelists. So now we will now return to the online survey. I invite the panelists as well to participate, and all of us. And we would like to ask you a few more questions. The objective is to gather your insight on the challenges and recommendations related to this topic. And we plan to use the result of this survey to draft a communication note about the event and to organize us for the next following discussions. So please reconnect to the Mentimeter with this QR code or directly on the menti.com. And Elisa, if you want to switch to the platform. So I'm also connecting. So excellent. So we are on this second section, vision on glacier groundwater challenges. And the first question is, what do you think is the most significant challenge linked to glacier retreat for water supply? So it's, you just enter, it's an open answer. So we talk a lot about water availability, but we have other challenges like water contamination, biodiversity loss. So please put your keywords there. So we see biodiversity loss, water quality. There is a lot of work showing that there are metals that are released. We have also CO2 that might also be released. So there is some feedback mechanism on the water quality that is quite important. Biodiversity loss. We will see all the biodiversity that are linked to this glaciarized environment that will migrate up, and at some point they won't be able to go up anymore. So yeah, clear threats on these aspects. And so some methodological also challenge related to how we estimate that. So thank you so much. We can move to the next question. So from your perspective, have you considered before the possibility of this groundwater interaction, glacier groundwater interaction, that these glacier retreats will actually impact groundwater resources availability and quality? So I think our audience is really expert on groundwater and hydrology. So we have mostly yes answers. So we have to consider that we do not sample the overall knowledge on these feedbacks, and I think we need to play a big role in raising awareness around the general public, the stakeholders, that these resources will be clearly impacted. So as it was discussed before, this goes with this critical zone observatories development and also this clear collaboration with local stakeholders. Thank you so much. We can move to the next one. So here is a different survey with, it's a scale, you can move around the bars. And we ask you, how do you think glacier retreat will impact the following services on mountain regions? So you have this scale from -5 to 5. -5 is strongly negative impact, +5 will be strongly positive impact, and 0 will be no impact. So mostly negative impacts, less on water quality. Thank you so much. So we can move to the next one, which concern mostly socioeconomic impact. So same question, but related to agriculture and irrigation, winter tourism, summer tourism, hydropower, community livelihood. So average remains in the negative impact. Thank you so much. Let's go to the next one. And two final questions related to your expectation. The first expectation is how do you consider the major, what do you consider the major unknown that scientists could help addressing regarding groundwater in glaciarized catchments? So here also open text, so you can write down your suggestions that we will further look at and eventually include in our next discussions. So I just need to inform you that it's already 11. It should be the end of this session, but we have just one more question to ask you. But of course, feel free to move to another side event. So there are many answers related to models, estimation of water volume, and link with also policy makers, transdisciplinary research in the light that we discussed before. So thank you so much. And finally, the last question is actually related to policy, and what is your main policy suggestion to improve groundwater management in high mountain regions? All right. So mainly related to monitoring local water uses, adapting water management strategy, as Bettina pointed out before, nature-based solutions for storing water in headwaters. Clearly, that's a very important aspect that we need to develop. Adaptation strategy, and involvement of education and public awareness. Thank you so much. That's very insightful. I think we can go back to the slides and conclude. So I just wanted to summarize the event very briefly. Thanks again to our panelists. You have shed lights on critical aspects related to glacier retreat and its impact on mountain groundwater resources, which is, as Bettina said, something that is not known, mostly through local studies. The global scale is a challenge. We lack data, we lack this holistic vision, and at the global scale in different contexts, but there are many actions and opportunities that are developing. We are moving fast now according to the emergency we are facing, so that's very encouraging. Thank you so much to the three of you for your participation, and we hope to continue this discussion further. The Mentimeter survey, so we were about 14 to 20 people, not a lot of, let's say, sampling across disciplines, but at least we have some ideas to further develop afterwards. Thank you so much for your participation. This result will be the base to continue the discussion. We will process that and identify the key topics that we actually just discussed for our next events. So the main event that we wanted to make you aware is a dedicated session at the European Geophysical Union in 2026, organized in Vienna, Austria, where we will deepen this discussion among the scientific community. As part of our Waterwise project, and with the University of Neuchâtel, we will organize a dedicated summer school where we plan to provide hands-on learning opportunities on groundwater in alpine or mountain areas for early career researchers and practitioners. So if you want to stay informed about these events, so we will post this on our social media. You can also sign to our mailing list just by sending a request to this email, projectwaterwise@gmail.com. And finally, I would like to thank all the organizers here present that have worked hard to make this 1 hour happening. And of course, the main organizer of the International Year for Glacier Preservation Launch Day for creating this opportunity. Well, thank you all for your participation, and we continue the discussion soon. Wish you a wonderful and inspiring day. Thank you so much. Bye-bye.